Hi guys, so here are we in the chapter 16 of Physics 191, and in this chapter we are going to learn about waves. You have already studied simple harmonic motion and oscillations basically in chapter 15, right, in the previous chapter, where you actually studied how you can look at a periodic motion of a particle, and we didn't actually go into the next part of what happens once you have created such a simple harmonic motion. So if you have a medium around it, um, what kind of phenomena, what kind of events you should be expecting coming out of those simple harmonic motion, right? So in general, in this chapter, we are going to study about the waves. And the waves are basically a consequence of, in some cases, or in most cases, if I want to say that, of a simple harmonic motion present in a certain medium. Now, of course, not always a simple harmonic motion will lead to waves. Generally, sometimes a small disturbance, a small non-equilibrium event could just generate uh, a wave in the system or in the material, right? So in order to understand waves, which is basically like transferring energy from one place to another through a medium, most of the times, not always, but in order to understand those, we will have to go to, or basically set up a model, which will call wave model. The wave model is basically built around a traveling wave. So you think about a wave that is moving from one place to another. When it does that, it basically carries energy with it. You're going to learn about waves also in the second part of this course, where you're going to see that there could be electromagnetic waves, right? So anyway, that's for later, but we will have to, for now, just remember that a wave always carries energy. If this is a mechanical wave, this will carry mechanical energy. If this is electromagnetic waves, it is going to carry electricity or electromagnetic energy with it. Now, of course, we don't have yet the model built, so let's just get started on that. So a traveling wave, which basically is like a very vaguely represented in this picture, is basically transfer of energy from the source of the disturbance, which is the center of this circle that you can see. And that's from that point that the wave is traveling, right, to the farthest point that it can reach. And the way it goes from one place to another, the way it transfers energy from one place to another is basically by making the material particles, making the water droplets basically going through simple harmonic motion, as we are going to see. So, but there are a couple things that we need to understand. All of these waves, all of these particles that are on this circle, they are very similar because they have the same phase when they are going through simple harmonic motion. And the nature of their simple harmonic motion, the equation that describes their simple harmonic motion are the same. Also, the wave moves in all directions. And if it was like a three-dimensional space, it would move like in 3 dimensions with the same wave speed, which is a well-defined wave speed in that material, right? So sound is also like a very similar kind of a wave that goes through a medium, and depending on the medium, it changes its speed. The medium of a mechanical wave is the substance through or along which the wave moves. It's very simple. If you have water, water is the medium. And if you have air, air is the medium. If you have an wooden block through which you are transferring sound energy or any kind of wave energy from one place to another, that would be the medium for that case, right? The disturbance is the rippling of the water surface. So that's basically the disturbance. So you have initially created the disturbance at the middle. Now, after each second passes, the disturbance is going to other places. The disturbance creates these ripples at other places, right? So basically, initially there was no ripple, there was no disturbance, there was no particle moving up and down, right? For example, if you look at this part of the water, the disturbance has not reached that part, meaning that it is undisturbed right now. Very soon, when this wave front is going to expand to this place, you are going to see another circle, a larger circle on which the so-called undisturbed water particles are going to get disturbance. And disturbance means basically, energy. It is going to get some energy, which was initially transferred from here. If you think of this as an work energy problem, you could even say that, okay, you had a pebble dropping from top, right? So it initially had a potential energy, and then the potential energy got converted into kinetic energy just before it was hitting the water. It had the maximum speed, so the maximum kinetic energy, and that kinetic energy is now transferred into water, the very, very central point of this circle. Once the water got the energy, now it is transferring the energy in all directions. And thereby, the water particles that are on the way, they are sharing that energy. They're getting part of it. And when they get that energy, what do they do? They basically go in like a vertical up and down motion. That's the vibration that you are seeing on the water surfaces. All right, so I think I took a little longer to describe this slide, but I think it's well worth it because we're going to go with some of these details in the next few slides, and I can actually make the discussions shorter in those cases if I need to. So a transverse wave is a wave in which the displacement is perpendicular to the direction of the in which the wave moves. In the previous slide, it was a transverse wave because the water particles going up and down in vertical line, but the wave is moving in this way, right? So if you look at, again, I'm taking a lot more time to this one, but it's worth it. If you look at the wave for this, this line, it is going along X, but the water particles are moving along Y, right? So this is a transverse wave. But you have other kind of waves as well, which we are going to see. So this is a transverse wave. You can see that the displacement is perpendicular to the direction of the motion of the wave itself. And then you have sometimes longitudinal waves. And longitudinal waves basically are the ones where you have the motion of the wave and the displacement. They're both in the same direction. So springs are like ideal examples of that, where you can see that the spring oscillates in this direction and the wave also moves in the same direction. So these are longitudinal waves. The speed of transverse waves on a string stretched with tension T is simply given by Ts over mu square root. Mu is the mass per unit length, and you are going to use this very, very often in solving problems with either waves or wave speeds or sometimes superposition of waves in the later part of this course. And anyway, this is called linear density or linear mass density sometimes because it's mass per unit length. We are going to use this later to find out more expressions with the wave speeds and harmonics, basically. Okay. Anyway, the next few slides are basically how you can represent pictorially a wave. When you are solving a problem, remember the ways we treated motion diagrams? This is the same thing. Just like motion diagrams, we are not going to always draw these snapshot graphs or wave history diagrams. We are going to only draw them when we need it. And in some cases, we will find out that it is impossible to solve a problem without drawing it. So we are going to do it, but we are going to use it as a flexible tool, okay? This is not like the free body diagrams. I generally will enforce drawing the free body diagrams, or anytime you are working with forces, I enforce that you should draw it. But for these guys, for the waves, if you are not, if this is something that you can work with just equations, that should be fine. For a wave on a string, but let's still understand it, that shows the wave's displacement as a function of position at a single instant of time is called a snapshot graph. So I think even if you don't read the whole sentence, just by looking at this line, this phrase, snapshot graph, should tell you what it is. It's basically a collection of pictures. Imagine if you have a camera and if you could take photographs of the wave traveling past you. What if you are taking like one picture every nanosecond or every like microsecond or something like that, what would happen? You are going to get a series of pictures, just like motion diagrams. You're going to get a series of pictures showing you where the wave is or has been or will be at certain instant of time, right? So that's all you would have to remember or understand the snapshot graphs for. So this is delta y versus x, right? So this is a graph of the string's displacement as a function of position at time t. So this is a graph of the string's displacement as a function of position. So any point, at any point, right? This is talking about the point at the position x. And this is basically telling you how much the x has displaced from its original position. So it's not only telling you which particle you're looking at on the string, it is also telling you how far it has moved from the equilibrium position. And the equilibrium position is this line. Okay. And eventually it is also going to tell you that how far it has been moving or at what speed it has been moving. Overall, the wave moves, right? The particle does not. The particle just goes from this place to this place and then it comes back, right? So that's what we are going to learn using snapshot graphs. And here are like a series of pictures. The wave moves horizontally, but the string particle moves only vertically, as I was saying, right? So you're looking at the X1 particle, one of the particles. Initially, if I have to draw, initially the string would look like this before anything started. And at that point, you are looking at, let's say, one of the particle which is at rest. Nothing is happening. And then at t1 instant of time, that same particle has moved at this much, right? So now you know how far it has moved, okay? How far it has moved in time t1, and that would be basically delta y1 or something. But this is only attributable. This is only talking about one of the particles. This is not like, if you know what is x1 doing, it doesn't mean that you necessarily know all of the different other particles that they're doing. You might need like separate information for them. But this is basically just talking about one of the particles, and remember, this particle is not doing anything apart from going in this direction, sorry, in this direction or in this direction, right? So basically, it is going to simply go in this plane, this line. It is going to create a vibration, and your snapshot is basically catching it at a certain point. It could be here, it could be here, it could be here, depending on time. It could be here. So at any instant of time, the snapshot graph is basically giving you one glimpse of what this guy is doing. Later on, you can see that, and this is basically, the X1 is basically now here, right? So this is basically like a longitudinal. The wave moves longitudinal, but the string particle moves vertically. But at this point, it has a larger displacement. At this point, the glimpse that you have taken is far from what it was before. At this point, it was this much. At this point, it was this much. So that's why your time and your delta y values has been changed. Don't get it wrong. This is not looking at a different particle. This is still the same particle, but the same particle now has a different delta y and a different t. All right. So combining these two, you get a new picture. And similarly, you get a new picture when it is again coming down, when it is again having a smaller displacement or smaller displacement from the equilibrium position. And it goes on and on until you complete a entire time period of oscillation. Okay, so again, the history graph or the snapshot diagrams, these are just for guidance. We are not going to use them if we don't need them. But it is good to be familiar with these concepts so that you can eventually use them, if you are in pressing need. And this is another representation. I don't know, sometimes I feel like this may give you, this may help you to understand the topic better. This may sometimes just confuse you. But I think what you have to take out from this slide is that how you should look at the wave travels, right? So imagine these are all ocean waves, right? So they all go in tandem, and overall, this is the wavefront. If this is the wavefront, then you have basically many of these guys traveling, and you have some parameters given along the t, you have some other parameters given along x. So you're basically looking at different, if you look at these time axis, you can see that it started like this and then it moved and moved and moved. So it's moving in that direction. So it's giving you a sense, if you merged all these diagrams together, what you're going to see is that your particle, if the particle was initially somewhere here, it has moved from here to here to here to here, and finally it is here, right? So all you're doing using this complicated diagram, you are saying that your particle has moved from this place to this place. Okay, so the arrow of travel of the wave is like this. And you get it from the times, right? So this is T1 or T initial. And if this is T final, you can say that between T initial and T final, you moved from here to here. And you are also talking about which particle you're looking at, right? So if you change the position of the wave, then you have to reposition your particle, but it's always talking about the same particle. So this same particle has moved from here to here. Here to here means here to basically here along the x-axis, right? So space-wise, the particle has moved from here to here. This is your xi, and this is your xf. And time-wise, this is ti and this is tf, because this is tf, right? So if you wanted to work with just a two-dimensional picture, it would look like this. This is your initial, this is your final. All right. Anyway, so again, use this. I would strongly recommend that you should watch these, look at these diagrams, and then you should watch the lecture video at the same time. Read the text that accompanies this diagram, because they will greatly emphasize the understanding part. So you should be good if you read it. Just by looking at this may not be the most useful way of understanding them. Visualizing a longitudinal wave. So you have snapshot graphs, and you can see that if you look at the medium, right? This is basically a medium. And this is looking at t equals to 0, 1, and 2 second position. So what's happening and in t and in x axis, right? What is happening when t equals to 0 and you're looking at x equals to 0, right? This guy basically. So at first you can see that and at t equals to 0, x equals to 0 is the starting point, right? So they are all coinciding. But as time increases, the x shifts more and more and more, and then comes back, right? So it's like a pendulum. If you think about simple pendulums, you would see that this is what is happening with the displacement. The displacement initially goes up and then it goes down. And that's exactly what you can see here, right? At t equals to 0, there was no displacement, then the displacement grows until it becomes 1, and then it shrinks again. It basically gets reduced all the way until 4 centimeter mark, and then it comes back to the negative, and then it goes again to the positive. So if you wanted to, you could actually draw a sinusoidal wave through this, right? And that should tell you that what you're seeing, a periodic function, is a periodic function. Now we are going to use more and more sophisticated techniques. We are not going to keep using our like diagram tools in order to describe this motion. We are going to use a diagram, a sketch, every time we have a wave problem, but then that's about it. You will draw a wave, and then you are going to use mostly mathematical equations to understand and solve problems on the basis of it. So in this one, this is basically a picture of a Mexican wave. They call it a Mexican wave because I think during the Soccer World Cup of 1986, Mexico World Cup soccer, they had this amazing phenomena or amazing display starting, which is spontaneous from the audience, spontaneous from the spectators who are in the stadium, and then, you know, just like water particles rising up and down, they kind of all in tandem went up and down in the same area of the audience, and that generated ripples. Like if you look at it from a very far away, from an helicopter, let's say, if you look at this, or from a TV camera, you are going to see that a wave is moving through the people of the stadium who are sitting over there. So that's like really an amazing spectacle. But most importantly is that we are talking, and when we are forming an equation, when we are going to work with a wave equation, we are going to talk about two kinds of length measurements. We are going to talk about the generic symbol d, which is the displacement of a wave at any type, right? D is basically the displacement at time t of a particle at position x. So imagine you have that same string, right? A string like a guitar string, which is attached to two rigid supports, and then you are closely watching one of the string particle. Okay, so that position of that particle is basically what we would call x. So you're looking at a particle which is at a distance x from origin, and then once we fix which one we are watching, we are going to work with only that particle. We will forget that there are other particles on the string. We're going to just say that, okay, whatever this guy does, everybody else will do the same thing with a different time lag, with a different phase. If these guys will do the same thing. So if we understand this, if we formulate an equation to describe this, we should be fine, right? So that's why your displacement or your d, which is the equation of the wave, will bring to you, will have the first argument is that which particle you're looking at. Which particle, the question is that you're looking at a particle, or the answer to that question is that you're looking at a particle which is at a distance of x from the origin, all right? The second piece of information is when this is happening. The second bit of information is at what time you are looking at this particle. So you're watching one of the particle on the wave media, one of the particle in the wave media that is oscillating back and forth, and you are watching it when you are describing it, you are going to say which particle is this, and you are going to also say when you have watched it, at what time you have taken the picture, basically, right? If you were taking all these snapshots. So let's move on. Once we have basically established what is a displacement, we can again look at the same picture, right? This is a wave source at x equals to 0 that oscillates with simple harmonic motion, generates a sinusoidal wave. So we have now moved forward. We have now moved away from our very vague and not so useful, sometimes counterintuitive wave discussion, where you had all those like triangular kind shaped waves moving, right? Instead, we now have like a proper wave, which is a sinusoidal periodic wave, that wave function that you can see here. And what we have decided that we would call these waves as consequences of simple harmonic motion. And that's like very understandable, right? Even thinking about the string, if you have a string and if you hold one part of it, and if you like basically move your hand up and down, and you can try this at home, then you're going to see that you are generating ripples in that string, right? Which we have been actually looking at so far indirectly. Now, that's exactly what we are going to say, that at x equals to 0, a wave source at x equals to 0 will just oscillate. It will just keep oscillating for some time. And then as an oscillation, as a consequence of that oscillation or the simple harmonic motion, you are going to see a wave being generated in the system, and it is propagating with time. So there are several parameters that you would probably need to remember as from your previous concepts, I think. One of them is time period. Time period is the time for one complete oscillation. And there are many different ways that you can look at the time period. If you start counting the wave from here, one complete wave is all the way until it comes back here, okay? So it's basically from here to here is your one time period. It doesn't mean that you cannot count time periods from other places. So if you are starting from here, right? So you would go all the way up and then you will come back, and then this should be your time period, right? So you have to look at the direction at this point. So this is the direction, right, of the wave. I mean, this is the direction at which you are counting, at least. So if you go from here, you will have to go until this point. And you can see no matter where you go, the time period has to be the same. If it is a regular sinusoidal wave, no matter where from you're calculating or where from you're counting, right? So the time period is a constant for a constant wave, for a wave which is not changing its nature or changing its direction or anything like that. The second thing is the amplitude. This is the amplitude, which is called A. You can see this is basically the maximum displacement that it can have, right? So you have learned time period. You have also learned frequency before. You know that from your rotational motion days, that frequency is just 1/t. Frequency is the number of complete oscillations it can do in 1 second. So if 1 second is from here to here, right, to here, one complete oscillation is just in 1 second. On the other hand, if this whole thing is 1 second, right, let's make it easy. 1, 2, 3, 4. If this is 1 second, then your frequency would be 1, 2, 3, 4 complete oscillations, or 4, right? So, and again, this doesn't have anything to do with our earlier understanding of what a time period is. But anyway, the point being, how many complete oscillations in 1 second you can make should give you what is the frequency. And in this case, we could not say, I mean, well, I guess, yeah, unless you know what is t, you can't say what a frequency is, but you can always look at and say, okay, this length in the time axis should be your time period. All right. Then you have the wave speed. Above is a snapshot graph for a sinusoidal wave showing the wave stretched out in space, moving to the right with speed v, right? This is the wave speed. You have a crest and a trough, and you can always find out wavelength the same way you found out the distance in the time axis to get the time period. Watch out for these changes, okay? This was talking about a d versus t. This is talking about a d versus x. So you're looking at the space coordinate. You're looking at the space coordinate, and if you have to understand this through the xt diagram, this is basically a good way to understand. If you are looking at your wavelength is basically this length, right? From here to here, one complete oscillation again. If you are looking at time period, that is totally different. Time period is along this axis, right? So time period is starting from here all the way it goes to until this point, right? So at what time this point is coming back to origin? If you go on, you're going to see that this is probably the second time this guy has traveled through the origin, right? So this could probably be your time period. It's quite complicated if you think about like this three-dimensional motion, and that's why it's much easier to work with 2D representations of them. But you should always pay attention to what you're looking at. Sometimes you will have the time axis to be the independent one. Sometimes you will have the x-axis to be the independent one. Okay, so again, there are like several of these sinusoidal waves. We'll try to make you understand how the wave speed is related to the oscillation itself. So here you have like at any certain point of time, like this is t equal to 0, right? So at t equal to 0, let's say the wave is like this. What will happen 1/4 time period? 1/4 time period, it will slightly shift from left to right, right? So now you have moved from this place to this place. Now you have basically, you can see the guiding line should tell you that this point is this point now, this point is this point now. So this point eventually has traveled this much, right? Along the x-axis. And it will continue to do that. The next time you see it, it will be here, right? So it's basically going back and forth on a vertical line. And then next time it is even farther and farther. So after like one complete time period, it looks exactly like where it started from. That's why it's like one complete oscillation. So this is like coming back to the initial position, and then it will continue to do this. So it's a very interesting thing to look at, graphically speaking, because all you are seeing is basically a simple pendulum, like oscillating back and forth in time. Okay. So at some point it started from here, and then it went like 1/4 time period, another 1/4 time period, another 1/4 time period, and then finally it is here. And it would basically come back, and then it would exactly look like, actually the 1/4 time period is this. So 1/4, another fourth, another fourth, another fourth, and it comes back to the initial position. Anyway, so let's move on. I think I'm going to stop with this slide and then come back to retrieve the rest of the concepts in subsequent segments. So the distance spanned by one cycle of the motion is called wavelength. We have seen it. Wavelength is measured in units of meters because it is a length. It is a length of one complete wave, right? One complete wave would generally, in my visual understanding, it would look like that it would start from one place and then it would go on, right? So this is the starting point, this is the ending point, this is a complete wave along the x-axis, right? So wavelength is along the x-axis and it is called lambda, and that has a unit of meters. If you do the same thing along t-axis, right? And that's why it is so important to understand, and that's why it's sometimes confusing. If you do the same thing along t, what you are going to see is the time period. And for that, the time period has a unit of seconds, okay? So because it's a time, this is a length, this is a time. So anyway, your wave speed is very easy to find out because it goes like lambda amount of distance in t amount of time. So if you want to find velocity, which is distance over time, right, or wave speed, which is distance over time, excuse me, then you get lambda over t, so v equals to lambda times f, because this is basically lambda times f, 1 over t is f, right, is your very important but very basic, very simple first equation of wave that connects speed, wave speed with wave frequency and wavelength, okay? So anyway, I'm going to stop here because it looks like we have spent a lot of time in going through the first 16 slides. There should probably be 2 more segments like this. And then of course, subsequent problem solving sessions that we will be having in between. Okay, so I'm going to stop here and then I'm going to see you in the second segment of chapter 16 discussions.